The next chapter is chapter 32 on Maxwell's equations and generally on electromagnetism. As you can see from this overview, we have 5 things to discuss: the Lorentz force equation, Gauss's law of electricity, Gauss's law of magnetism, the Faraday law of induction, and Ampere's law modified by Maxwell. These are the 4 Maxwell's equations right here, and they're augmented by the Lorentz force equation, which I'll begin with. So this will be section 32.1 in chapter 32. If we think generally about having charged particles moving around, here's the negative charge and a positive charge and another positive charge, as they move around, we recall that the positive charges have an electric field that goes out from them, and the negative charges have an electric field that comes into them. And as these charges move and have a velocity going in some direction, they also create a magnetic field according to the right-hand rule around them. So in general, charges by their position create an electric field, and by their motion create a magnetic field B. These electric and magnetic fields permeate the space and act upon the other charges. The electric and magnetic field generated by a charge do not act back on that same charge again. However, they do act on other charges. So what we do is we break the problem up into 2 parts. The first part is, if we know for a given particle, like here's the negative charge right here, if we know what the electric and magnetic fields are from other charges at that point, then we can write the force on that particle as Q times the electric field plus Q V cross the magnetic field, where V is the velocity of the particle as it moves somewhere, B is the magnetic field at the point where the particle is, and E is the electric field. Q is the charge that the particle has on it, assuming a positive charge here, and this force, of course, is a vector. This force gives us dp dt by Newton's second law, and so this equation right here is called the Lorentz force equation, and complements the 4 laws of Maxwell that we're getting ready to discuss. Basically, what we have done is we have broken up this action at a distance into 2 parts. We have said, and let me redraw this, here are 2 particles, and there's a force between them according to Coulomb's law, which is F is equal to K Q1 Q2 over R squared, as we've already discussed. But people were concerned about this concept. They said, how can this particle reach across a vacuum and exert a force on this particle over here? And so, as we discussed earlier, they broke this problem up into 2 parts. They said, well, this particle here creates an electric field, and this electric field permeates the entire universe. This particle over here finds itself in the electric field of these other particles and experiences a force. Therefore, what happened was, in this force equation, we broke it up into, if we call this Q2 and this Q1, we broke it up into 2 parts, a Q1, a charge, times K Q2 over R squared, and said, this is the field, this is the electric field, and this is the charge that finds itself in that electric field. And so you can see we've really split the equation that Coulomb provided us with into 2 parts, an electric field part and a charge part. And so now we can write this as Q times E. Then later on we found that there was another force that comes from the magnetic field when a charge is moving. And so that added to this, giving rise to the full form of the Lorentz force equation. So dp dt, the time rate of change of momentum, is always equal to the force by Newton's second law, and by electromagnetism, that force is equal to Q times E plus Q V cross B. From this, we can find the force and thereby the change in momentum of any particle that has a charge Q and is moving an electric and magnetic field. Well, next we're going to discuss the four equations, and just as a precursor to that, let me mention that over 100 years were devoted by many scientists to understanding from Coulomb, the electric field, the magnetic field, the forces that they exerted on each other, the changes in the magnetic field, and so forth. So if we look at the electric and the magnetic field, we can say, how do they arise? Well, they arise from charges. They arise from electrical currents when particles move, like this charge here that's moving with a velocity v. But they can also arise, as we found, where the electric field can be generated by a changing magnetic field, and a changing magnetic field generated by electric field. So now let's review the forms that we have found for these equations.